Over 70% of our planet's surface is covered in oceanic water. We live on a world of absolute, overwhelming liquid abundance. Yet millions of people wait in lines every day to secure enough safe water to survive. Proximity to the ocean does not guarantee hydration. The barrier is chemical. Seawater is heavily loaded with dissolved ions like sodium and chloride. If ingested, this dense salt concentration actually pulls moisture out of human cells, making it toxic to drink. To resolve this massive macroscopic water shortage, engineers first have to manipulate physical laws down at the microscopic level. In osmosis, pure solvent naturally flows across a semipermeable membrane to dilute a salty solution. To extract pure water, we apply immense mechanical pressure, overpowering nature's flow, forcing water strictly backward. The microscopic filter lets water molecules squeeze through, completely blocking larger salt ions. This intervention is known as reverse osmosis. It is the mechanical workhorse driving the massive desalination plants that produce drinking water for entire countries. But designing a plant of this scale requires engineers to calculate exactly how much pressure to push against the seawater, and that is exactly where the math breaks down. Osmotic pressure is what chemists refer to as a colligative property. This means its entire calculation relies on the total number of solute particles floating in the water, not the specific chemical identity of those particles. Standard scientific calculations assume a clean 1-to-1 ratio. If you dissolve 1 mole of a compound into water, you expect exactly 1 mole of individual particles to exist in the solution. Ionic compounds ignore that assumption. Take potassium chloride. When dropped into water, the molecules don't stay together. They dissociate, splitting entirely into separate potassium cations and chloride anions. Because the solution now holds exactly double the expected number of particles, any textbook calculation ignoring the split will fail. The experimentally derived molar mass artificially halves, resulting in a wildly inaccurate, abnormal molar mass. Ignoring this invisible dissociation guarantees disastrous miscalculations. Engineers relying on those broken numbers wouldn't apply enough force to push seawater through a desalination membrane. The particle count problem also happens in reverse. Some molecules actually clump together in a solution, like ethanoic acid dissolved in benzene. Because benzene has a low dielectric constant and doesn't insulate charges well, hydrogen bonding takes over. The ethanoic acid molecules undergo dimerization, actively pairing up with each other. 2 particles become 1. The individual particle count halves, which artificially doubles the resulting experimental molar mass, creating another massive anomaly. Whether the molecules are splitting apart or clamping together, standard chemical blueprints are blind to the true particle count in a solution. In 1880, a Dutch chemist named Jacobus Henricus van Hoff solved this calculation crisis using a single elegant variable. He introduced the Hoff Factor, represented by the lowercase letter I. It provides the exact mathematical ratio between the normal expected molar mass and the abnormal observed molar mass. Functionally, I acts as a simple multiplier, representing the true particle count. For dissociating potassium chloride, I approaches 2. For associating ethanoic acid, I drops to 0.5. This one factor corrects the microscopic chaos occurring inside the liquid, snapping theoretical math perfectly back into alignment with reality. To make accurate predictions, the Hoff factor must be permanently inserted into all the standard colligative property equations. It corrects the relative lowering of vapor pressure, the elevation of boiling point, the depression of freezing point, and critically, the calculation for osmotic pressure. With these corrected formulas, engineers have the exact blueprints needed to calculate the necessary mechanical force, push massive volumes of salt water through a membrane, and safely filter out the toxic ions. These whiteboard calculations provide the exact engineering required to quench human thirst, turning the surrounding oceans into a viable source of survival.